So, good morning, everyone, and thank you for being here today. My name is Heshan Pereira, and I'm going to talking to about foundation of computing. Over the next few minutes, we are going to explore three big areas that form backbone of every computer system we use. So, computer hardware, how data is represented digitally, and how networks connect our device together. So, these topics might sound technical, but by the end of this presentation, you will have a clear practical understanding of how your laptop, your phone, and even the internet itself actually behind the scenes. So let's get started. So let's begin with the first main section of this presentation, which is a computer hardware. In this part, I will cover four key areas. So first, I will explain the basic components inside the CPU, which is often called the brain of the CPU. So second, I will walk you through the role of the CPU plays when it comes process information. So thirdly, we will look at how different hardware components works together as a system. So because no single part of a computer works in isolation. So finally, I will introduce the different types of storage media we use to save our data. So, from the memory inside your computer to the external drives you might carry in your bag. So, let's start with the CPU itself. Okay, let's talk about basic components of the CPU. The CPU or central processing unit is not just a single part. It's actually made up of several smaller components that work closely together. So, the first is the control unit. Think of control unit as a traffic officer standing in the middle of the busy intersection. So it doesn't do the calculation itself, but it directs the flow of data and makes sure every other part of the CPU works in the correct order at correct times, right? So next we have arithmetic logic unit or ALU. So this is the where the actual maths happen, right? So arithmetic logic unit performs calculation like addition, subtraction, and it also carrying out logical operations. So such as comparing two values to decide which one is bigger. So then we have registers which are extremely but very fast storage areas inside the CPU. So you can imagine registers as a worker's hands, right? So holding just a few items at a time so they can be used immediately. So rather than working back and forth to a warehouse. So there's also chase memory, a type of high-speed memory placed very close to CPU, which stores information that is used too frequently. So the CPU doesn't waste time fetching the same data again and again. So finally, and clock keeps everything synchronized. So it generates regular electronic process that tell the CPU exactly when to perform each step, similar to a metronome, keeping a band playing in the game. So together, these few components allow the CPU to process billions of instructions every second. Okay, now that we know what's inside the CPU, so let's talk about what it actually does. The CPU follows a repeating cycle to process every single instruction, and this cycle has several stages. The first stage is called fetch, where the CPU collects an instruction from memory before any processing begins. So next come decode, where that instruction is analyzed. So the CPU can understand exactly what action needs to be performed. After that is execute, where the required task is actually carrying out, whether that's a calculation or logical operation. So alongside this, CPU is constantly performing control and coordination, managing and directing all of the computer's operations so that everything happens in the correct order. It also handles data processing, working through calculations, comparisons, and decisions as the information passes through it. So, and finally, there's the stage where the process result is saved either in memory or back into the register, ready to be used later. So this entire sequence fetch, decode, execute, and store happens over and over millions times of per second, and it's essentially the heartbeat of computer. So, so now let's zoom out a little and look at how all the hardware components in the computer work as a team. So because the CPU can't do everything alone, right? So it all start with input devices like a keyboard or mouse, which are used to enter data and commands into the computer. That information is then sent to the CPU, which process and the data and control the main operation of the machine, right? So while programs are running, the computer use RAM to hold data temporarily, giving back quick access whatever is currently in use. So for anything that needs to be kept permanently, like your files, photos, or installed programs, the computer relies on storage devices such as hard drives or SSDs. So all of these components are physically connected to the motherboard, which act like the skeleton of this computer. So linking every part together, data actually travels between these parts using the bus systems. So which transfers signals between the CPU, memory, and other devices, almost like a highway carrying traffic between different parts of the city. So and finally, once everything has been proceeded, the result is shown us to us through input devices such as a monitor, a speaker, a printer. So in short, input goes in a CPU and RAM process it. Storage keeps it safe, and output devices show us the final result. So, so this diagram bring together everything we have just discussed. So you can see how the input devices, the CPU, RAM, storage, and output devices are all connected to the motherboard and the bus system, right? So I wanted to include this visual because it's much easier to understand hardware architecture when you can actually see how the pieces connect rather than just hearing about them separately. Now that we have solid picture of the computer hardware, let's move to look more closely at storage stand starting with the fastest types of memory a computer uses. So let's talk about primary usage. So which refers to the memory a computer uses while it's actually running. So the first type is a RAM or random access memory. Random random access memory temporarily stores data while your programs are open and running. It's important to understand that RAM is volatile, which means that as soon as you turn off your computer, everything stored in the RAM disappears. However, but RAM lacks it for performance. It makes up for in speed. It's much faster than other types of storage, which is why having more RAM usually makes your computer feels more responsive. So the second type is ROM. It's a read-only memory. Unlike RAM, RAM is a non-volatile, which means the information stays even after the power is switched off. So RAM commonly stores firmware such as BIOS or UEFI. So which are small programs that run the moment you turn on your computer. Without ROM, your computer wouldn't even uh, know how to being the starter process. Finally, we have cache memory, so which we touched on earlier. It sits extremely close to the CPU and stores instructions and data that are used most often, so the processor can access them almost instantly without waiting for slower memory. So now let's move on the secondary storage, which is used for keeping data long time. Even when the computer is switched off, the first example is the hard drive or hard disk. An hard drive stores data on a magnetic disk and spins rapidly inside the drive, and it's typically used for long-term storage of large files and large applications. So its biggest advantage is that it can store huge amount of data at a relatively low cost, which is why hard drives are often used for storing things like movies and games. So next we have CDs and DVDs, uh, optical discs, so which stores and using less technology, and these were commonly used for software installation, so playing media and creating backups, although they have fairly limited storage capacities compared to modern options. So, and today we mostly see them used for things like music CDs or older software installations. So, finally, there's the SSDs, or it's called solid state drives, right? So which stores data using flash memory instead of spinning disks. So because SSD have no more moving parts, they are significantly faster and quieter and more durable than hard drives. So this is why SSD are now used for fast storage in com- modern computers and laptops, especially for things like operating systems or games that need to load quickly. So another important category is removable storage, which refers to device you can easily plug in, unplug, can uh, carry around, right? So the most familiar example is the USB flash drive, right? A small portable storage device with capacities that now range anywhere from 8 gigabytes to 1 terabytes, right? So its main purpose is to tell you store, transfer, and backup files quickly. It's a commonly used for documents, photos, and videos, right? So next are memory cards, which are also portable flash storage devices, typically ranging from uh, 16 gigabytes to over 1 terabytes, right? So these are especially used for expanding storage on devices like DSL cameras. So where they used to save high resolution photos and videos while recording, right? So finally, we have external storage devices such as external hard drives, SSDs, so which offer much larger capacities from 500 gigabytes up to 8 terabytes, right? So or more, right? And these are ideal for tasks that require transferring large amount of data, such as video editing files or extensive game libraries. So now that we have covered hardware and storage in detail, let's move on the second major part of this presentation, which is all about computer represent information digitally. So next section is going to look at how computers actually represent the information we use every day, right? Whether that's text, images, sound, or secure data, I will walk you through 5 topics. First, how data is represented inside the uh, computer using binary. Second, how encryption keeps our data secure. Thirdly, how images and audio are digitally represented. And how compressions help us reduce file sizes. And finally, I will briefly introduce logic gates, which from uh, in the physical foundation that makes all of this possible. So let's start it right at the very core of how computers think with binary numbers. So okay, let's talk about binary number representation. So at the deepest level, every computer only understand two values, right? 0 and 1. This is a old binary system. It might seem surprising, but all types of data, including text, images, and sounds, audio, are eventually converted to a combination of these two digits before a computer can process them, right? So, to understand this better, let's talk about bits and bytes. A bit is the small possible unit of data, and it can only be 0 or 1. So when you group 8 bits together, you get 1 byte, which is commonly used to represent a single character, like a letter A, right? So from there, storage capacity is measured in large units such as kilobytes, megabytes, gigabytes, and also terabytes. So which is the terms like KB, MB, GB, and TB come from here. So beyond simple bits, computers also need way to represent more complex numbers. So negative numbers are commonly stored using a method so called two's complement representation. So like that, yeah. Which allows the CPU to perform subtraction using only addition circuits. So we can say real number meanings with decimal points are represented using floating point format, which allows computers to every large or very small numbers with a good level precisions. So all of this method together allow mm, something as simple as zeros and ones to represent the entire digital world interact with every day. So this slide gives a visual summary of what we just discussed, showing how binary digits combines to form bytes, right? And those bytes are used to represent numbers and characters. Since this laid out visually really helps reinforce just how much complexity can be built from something as simple as two digits. So with that foundation in place, let's move on topic that relies heavily on binary representation, which is encryption and data security. So let's talk about encryption and data security. Uh, which one is the most important concept in the modern data security? So in simple terms, encryption converts readable information into a secure coded format, right? So once data has been encrypted, it cannot be understood without the correct decryption key. Like so, even if someone manage get hold of it, this is why encryption is so widely used. So it prevent data uh, left by making stolen files completely unreadable to hackers, and it also secures online communication. So such as private chats and online shopping transactions. So how does it actually work? So we can say the original readable data is called plain text, right? So which is essentially the starting messages. So the plain text is then transformed into ciphertext, a scrambled version of the message that can be safely sent over network, right? So decryption is the process that we reverses this transformation using the correct key, restoring the original message, right? So let's look at the simple example using something called a shift cipher. So with a shift of 3, imagine our plain text is the word secret, right? So using a secret key of plus 3, meaning we move each letter forward by 3 positions in the alphabet. So the word secret becomes ciphertext VHFUHW. So to decrypt it and read the original word again, you simply shift each letter backward by three positions. Of course, real world encryption used today, like the kind of protects your online banking, is far more mathematically complex than this simple example, but the basic idea transforming readable data into unreadable data. So I'm back again using a key remaining exactly the same way. Okay, let's move on to how computer represent images digitally. So every digital image is a made up pixel arranged in a grid, right? And a pixel is a simply tiny and secure that together with thousands or millions of others make up a full picture, right? So individual picture has a shade value which is stored in binary. You can get example of that. The binary value uh, 11001010 might correspond to number 202, which represent a specific shade of the gray. This is bring us to image resolution, which refers to the numbers of pixel in width multiplied by height, such as 1920 by 1080 for a full HD image. The general rule is that higher resolution gives you smoother shading and more visual detail, but it also results in a bigger file size since there's simply a more pixel data to store. So different file formats handle this trade-off in different ways. So JPEG files have a small file size but loss a uh, little quality due to compressions. So PNG files preserve perfect quality and support transparent backgrounds, right? So which is why they are uh, often used for logos. So and BMP files store completely uncompressed. So raw data, which is result in a huge file size. So let's also look briefly at grayscale color representation. So where shades are stored using a single brightness value ranging from 0 to 255. So a value of 0 represent pure black, right? So 100, sorry, 128 represent medium green and 255 represent pure white. To put this all together, imagine 100 by pixel grayscale image, right? So that image contains exactly 10,000 pixels, and each one of those pixels stores an 8-bit shade values in binary. So which shows just how much data even small simple image actually contains. Okay, now that we understand how much data images and audio actually require, uh, it makes sense to talk about compressions, right? So which is the process of decreasing file size so that we files use less storage space, right? So beyond just saving space, compressions also helps file transfer saved and open more quickly, which is especially important when you are sending files over the internet. So there are two main categories of compressions. The first is lossless compressions, which keeps all of the original information without removing any data at all. Uh, this means a file can be restored exactly as it was before compression with absolutely no less inequality, right? So common example include the gift, uh, TIFF and zip files, right? So the second category is lossy compressions, right? So which removes unnecessary or less noticeable data in order to reduce file size right. So this type is mostly used for photos, musics, and videos files, right? So where a small, uh, often unnoticeable reduction in quality is an acceptable trade-off for a much smaller file size, right? So family example here include JPEG images and MP3, MP4 videos files. So, so why does compression matter so much in practice? It helps free up storage space on your computer and mobile devices. So, and it also improve download and upload speeds, which is something we all benefit from every time we stream a video or send a files online. Okay, now that we understand how much data, images, and audio actually require, uh, it makes sense to talk about compressions, right? So which is the process of decreasing file size so that we files use less storage space, right? So beyond just saving space, compressions also helps file transfer saved and open more quickly, which is especially important when you are sending files over the internet. So there are two main categories of compressions. The first is lossless compressions, which keeps all of the original information without removing any data at all. Uh, this means a file can be restored exactly as it was before compression with absolutely no less inequality, right? So common example include the gift, uh, TIFF, and zip files, right? So the second category is lossy compressions, right? So which removes unnecessary or less noticeable data in order to reduce file size right. So this type is mostly used for photos, musics, and videos files, right? So where a small, uh, often unnoticeable reduction in quality is an acceptable trade-off for a much smaller file size, right? So family example here include JPEG images and MP3, MP4 videos files. So, so why does compression matter so much in practice? It helps free up storage space on your computer and mobile devices. So, and it also improve download and upload speeds, which is something we all benefit from every time we stream a video or send a files online. So let's now go one level deep and look at logic gates. So which are the basics building blocks using the all digital electronic systems, right? So logic gates receive binary inputs, meaning combination of zeros and ones. And based on those CPU, those inputs, they produce a single binary output. So why do logic gates matter so much? They are responsible for carrying out logical and arithmetic operations inside every digital system, right? So and they help computers process information and make decisions even at the most basic hardware level, right? So in fact, logic gates from the foundation of software application and virtually uh, every modern electronic devices we use, from smartphones uh, to washing machines. Every complex operations a computer performs, no matter how advanced, ultimately breaks down into millions of simple decisions made by logic gate like these. So this slide gives a visual overview of how these logic gates represent how they combine to form more complex circuits, right? See in the actual symbols and structures helps make an otherwise abstract concept feel much more concrete, right? So with that, we have now completed our look at how computers represent data from binary numbers to encryption to images, audio compressions, and logic gates. Now, let's shift our focus to the third and finally major topic of this presentation, computer networking. Okay, so guys, in this final section, we are going to explore how computers connected and communicate with another, right? So I will cover four main areas. First, uh, the different categories of computer networks based on the size of area they cover. Second, the essential networking hardware, software, um, and communication media that make networking possible, right? So third, we will explore the basics of internet and web technologies, right? So which power the website we use every day, right? So and finally, we will look at different network topologies, meaning the different ways devices can be physically or logically arranged within a network, right? So let's begin by look at how network are categorized. Okay, computer networks exist connect computers and smart devices so they can exchange information and resources, allowing users to communicate, right? So access shared files and use network service more efficiently. Uh, networks are generally networks are generally categorized by the size of the area they cover, right? So let's start the largest scale, the mm, WAN or wide area network. A WAN connects devices across cities and even entire countries, and its purpose is to enable communication between mm, different lands over long distance, right? So in fact, uh, the internet itself is the largest WAN extends connecting network globally, right? So on a small scale, we have a LAN local area network. A LAN connects devices within a limited area, right? So such as a home, an office, or a school, right? So its purpose is to allow users shared files, printers, and internet access locally. So a good example of this would be all the computers connected within a school computer laboratory, mm, which can share the printer and internet connection without mm, needing to reach outside the building. So yeah. Okay, guys, let's continue looking at network categories, right? So this time moving a smaller and mid-sized networks. First, there's the PAN or personal area network, which covers a very short distance around a single person, right? So usually within a 10 meters. Sorry, that yeah. Its purpose is to connect personal device for easy data sharing and communication. And a perfect everyday example is the Bluetooth connection between your phone and your wireless earbuds, right? Uh, next is the metropolitan area network. So which covers a city or large metropolitan area, right? So its purpose is to connect multiple lands within same city, uh, more efficient communication, right? So such as several universities campuses connected together across a city, right? So why does networking matters so much in the first place? Computer networking offers several key benefits, right? So it uh, allows for easy file sharing. So users can quickly share files with one another, right? So it enable remote access, meaning users can securely access files and systems from a location entirely different location, right? Uh, and it provides better security since network administrators can control exactly who has access to the network and protect sensitive data more efficiently uh, than if every device operated in isolation. So now that we understand the different types of networks, like um let's look at the what's actually needed. Build one. So this start with network hardware, which consists of physical equipment used to connect computers and other digital devices. So this hardware enable devices to exchange and data supports communication across the entire network. Without physical hardware like this, none of the network types we just discussed, whether PAN, LAN, MAN, or WAN, right? So would actually be able to function. So uh, let's look more closely at the specific device that make up network hardware, right? So first we have the switch, right, which connect multiple devices within the same LAN and importantly sends data only to its correct destination rather than to every device, right? So compare that to a hub, right, which also connect several devices but instead broadcast data to every single connected port, uh, whether that devices needed the data or not, which makes it far less efficient than a switch. So next is the router, which connect different networks together and forward data between them. A very common example is a router connecting your home network to the internet. We also have a network interface card or NIC, which allows computer or device access communicate on a network with the first place. And finally, there's the modern uh, which converts signal between your internet service provider or ISP um, and your home or office network to see how these devices typically work together. Consider this example. For the connection start at the internet, the passes through modem, then router, then possibly wireless access point or Wi-Fi router before finally reaching individual devices that laptop and phones. So this diagram illustrate how these different hardware devices, the modem, mm, router, switch, and access point, are physically connected together in a typical network setup, right? So visualizing this flow make it much easier to understand how data actually travels from the wider internet all the way down to the device in your hand. So now that we have covered the physical hardware, let's shift our attention to the software sides of networking. So while hardware provides the physical connections, network software is what actually control, manage, and protects those connections. So in simple terms, network software is a collection of programs that helps devices communicate. So share resources and exchange data efficiently. Um, there are several important functions that network software performs: security software projects the network from unauthorized access, and common examples include firewalls, antivirus programs, right? So communication protocol software users establish standards such as TCP, uh, HTTP, and SMTP to enable reliable data exchange between devices. Network monitoring software tracks networking performance, detects faults, and alerts administrators whenever problem areas. So, a network operating system controls network users shared resources, with Linux server being a common example, right? So, Linux is a very famous for hackings, right? So, and resources management software uh, manages shared printers, storage, and other network resources to pro of this uh, together. Imagine a typical office network, right? So the network operating system manage users accounts and shared folders. Security software actively blocks cyber threats they appear, and monitoring tools continuously make sure everything runs smoothly, right? So this combination of hardware and software is really what keeps modern networks reliable and secure. So guys, next slide is a communication media. You can call it a transmission media. So like that. Okay. Sometimes all called transmission media. This refers to the channels that actually carry data between network devices, whether that's through physical cables or wireless signals. So communication media is what enable computers and other devices to exchange information quickly and reliably. So connecting everything we have discussed so far, the hardware and software, into a functioning network. Without a reliable medium to carry the signal, even the best hardware and software wouldn't be able to communicate at all. Okay, guys. Now let's move into the one of the most relevant topic for anyone using the internet today: web technologies. Web technologies refers to the tools, programming languages, and standard used to create and run websites and website applications, right? So they make it possible for users to access, interact with, and share information on the internet, right? So let's look at the main web technologies that make it happen. HTML, which is standard for hypertext markup language, creates the basic structure of a web page. So it defines elements such as a heading, paragraphs, images, links, and tables. So essentially, forming the skeleton of every website you visit. Next, CSS controls the appearance of web pages, adding colors, fonts, layout, spacing, responsive designs patterns that just a website for different screen sizes. So then there's JavaScript, which makes websites interactive. It's used for things like buttons, forms, animations, sliders, and real-time updates. So, which is modern, which is why modern websites feel dynamic rather than static. So, finally, behind every website, there's a web server, which stores the website's files and delivers them to users through the internet. The web server processes requests mm, from web browsers, essentially uh, responding every time you type a web address, hit enter. Okay, guys. Web technology supports websites, right? So online servers, e-commerce platforms, and social networking, and they continuously improve website speed, security, performance, and overall user experience. So let's look at a few more essential technologies that support the modern web. So first, there's the database, right? So which stores and organizes website information such as user accounts, products, and orders, essentially acting as the memory of a website, right? So next we have uh, HTTP and HTTPS, which are protocols used to transfer information between web browsers and web servers, right? So HTTP specifically encrypts and data during that transfer, providing secure information, secure communication. Sorry for that, which is especially import whenever you are entering passwords or payment details online. So think about that. So then there's the content management system, right? So or CMs, mm, CMS, which is software used to create and manage website content easily without needing advanced coding knowledge, right? So a well-known example of the WordPress. And finally, we have APIs or application programming interfaces, which allow different applications and web servers to exchange information with one another. Right. So a great real world example is payment processing API. So which connects and only stores to a secure payment service, allowing you to check out safely without the stores itself needing to handle your card details directly. So yeah, together these technologies from the invisible structure and yeah, behind almost every website and we use daily. So, okay, guys, let's move on to our final major concept. It's network topology. Network topology is the physical or logical arrangement of devices in a computer network. So, and it determines how devices communicate, transfer data, and maintain performance across the network, right? So let's look at three basic topologies. First one is a bus topology, where all devices share a single communication cable. So its purpose is to provide a simple and how low cost setup for small networks. And a typical example would be a small office network using the one shared cable. So second, star topology, where every device connected to a central switch or hub. This make it easy to manage, expand the network. So since adding or removing a device only affect that one connection point. A good example is a school computer lab connected through a central switch, right? So and thirdly, ring topology, where devices are linked in a circular path, passing data from one device to uh, the next around ring. Here are there. This provide orderly and reliable data transfer. An example would be a factory network using a ring connection for consistent, predictable data flow along the production line. So, okay, guys, let's talk about advanced topologies. Beyond the three basic topologies, there are also more advanced arrangement used in larger or more demanding networks, right? So, mesh topology is the one where every device is directly connected with the multiple other devices. So this provide highly reliable communication with the multiple data paths. So meaning that if one connection fails, they can still travel through another route. So this is why mesh topologies often use military communication networks. So where reliability is absolutely critical, right? So there's also hybrid topology which combines two more different network topology together. So this offers greater flexibility for large complex networks. And a good example would be a university network that uses both Starburst topology in a different parts of its campus, right? So why does network topology matter so much? Choosing the right topology improves overall network performance and supports future and network expansion. So which is an important consideration for many organizations planning to grow. So guys, to bring everything together, we have covered a lot of ground today. So we started by exploring computer hardware, looking at the CPU and its core components, and how the CPU processor instructions through the fetch, decode, execute, and store cycle, and different types of storage available to us, and from fast RAM and cache, to long term hard drives, SSDs, and portable removable storage. So we then move into the computers representing information digitally, starting with the binary numbers and bytes. So moving through encryption and data security, mm, digital images and audio, file compressions, and finally logic gates that make all of this basically f- possible at the hardware level. So finally, we are exploring computer networking, covering the diverse categories of networking from PAN and WAN, the hardware and software that makes networking possible, the basic internet and web technologies that power website we use every day, right? And the different network topologies that determines uh, how devices are arranged and connected together. So these three areas, hardware and data presentation, data representation, and networking, from the true foundation of computing. So yeah, and understanding them gives us a much deeper so appreciation for the network topology technology. Mm, we really on every single day. So yeah, thank you all so much for your attention today, and I hope this presentation has given you a clear idea about foundation of computing. So yeah, I would happy about answering questions you might have. So yeah, thank you.